In this presentation, we're going to explore some of the more practical uses of UV spectroscopy in a research lab that you might be working in. As you might have got the impression from my previous presentation, I sort of made the case that UV spectroscopy is useful, but that for structural determination, we tend not to lean on it too much. In the last presentation, we talked about how UV spectra absorbs, like the theoretical reasons for this, the nature of the sigma bonding to antibonding transitions, the pi bonding to antibonding transitions, and the non-bonding orbital to antibonding orbital. Here's an example of N to pi star transitions that we can see in the UV spectrum, and how we can interpret these. And basically, it tells us that we have systems with conjugated bonds and the extent of those conjugated bonds. We looked at these sort of structures containing only sigma bonds and containing pi systems and containing conjugated pi systems, and we were able to understand why the absorbances turned out the way they did. But none of this really helps us to nail down the detailed structure of a molecule. We can kind of just get hints of its electronic structure. So what's it good for? Well, one thing you can do is there's books of tables of calculations you can do to predict maximum absorbance, and if you understand the absorbance of and the mechanisms of this, if you're sort of a true physical chemist, you can sort of calculate what the UV spectrum might be for an unknown molecule. Of course, if you have it in your hands, you can get the UV spectrum. And then what would you use UV spectra for? Well, let's say there was an unknown gas in the atmosphere. Well, you can't do NMR in the atmosphere, but you can predict the extinction coefficient and maximum absorbance peak of molecules using the Woodward-Fieser rules and lots of other rules that have been developed for UV spectroscopy. Those rules are briefly explained in your textbook. I'm not going to go through them now because we're really not going to use UV spectroscopy for structural elucidation in this course. But I do want to make the case that it is useful. You have a UV spectrometer in your lab, or I guarantee you, if it's not in your lab, it's next door. Why do we have them? Because they are extremely useful. So one thing you can do is, if you already know the spectra, you can use it for identification. So kind of like fingerprints, except with less detail. So most instruments can give us the spectrum from about 180 all the way up to 800 nanometers. And that really just gives us these sort of conjugated systems here. So we can get these alkene systems here and conjugated alkenes. And then, of course, there's the forbidden transitions in carbonyl groups, which will show up over here. So there's lots of information. Now, if you had really extensively conjugated molecules, say, for example, like this chlorophyll, methylene blue dye, beta-carotene, your absorbances, of course, are going to find themselves up here in these higher wavelengths, which are easier to see. So how would we know if we had chlorophyll or beta-carotene? Well, you'll be able to tell just by looking with your eyes, but we know the spectra of these molecules, so let's sort of see what we can glean from that. Here's beta-carotene, of course famous for being in carrots, and if you chop it in half you get retinal, which of course is essential cofactor for vision in our rods and cones. There's the UV spectrum for UV-vis spectrum for beta-carotene, and notice that, remember, this is a log scale here. Absorbance is a log scale, so we have 100-fold difference in absorbance between the peak and say around here. So we're absorbing 100 times more light around 450 than we are around 500. And if you look at the visible spectrum, you can see how we're absorbing way more of the blue and green light, and then there's 100 times more of the blue light being absorbed than higher frequencies, which is why beta-carotene generally appears to be orangey red. There's methylene blue. It has a different electronic structure, so we could expect a different UV-vis spectra. And of course, we'd be able to tell the difference between the two molecules just by looking at the spectra. There's the spectra for methylene blue. And here we see it's 100 times more, has 100 times more absorptivity up here in the higher wavelengths compared to the lower wavelengths. It's absorbing much more red than blue. And so I expect it to look blue, and guess what? Blue is in the name. Chlorophyll. I think we know what color to expect there. Here's the spectrum, and you can see it absorbs 100 times more in the blue compared to the blue-green, and then there's sort of this space in the middle, and then it absorbs strongly at the lower wavelengths as well. So it's cutting out the blue, it's cutting out the red. What's left? The green. So if we had all of these molecules, we'd be able to compare their spectra, and you'd know which one you had. And Another thing I'd like to point out is that notice how chlorophyll has a slightly different spectrum in a highly polar solvent like methanol compared to a slightly less polar one like ether. So solvent will affect UV absorption because solvent, of course, affects the molecular orbitals of a molecule. If you've got a lot of dipole stabilization, you're going to have different molecular orbital energy levels than if you have none of that. So solvent can affect UV spectra, so always keep that in mind. So if I already know the spectrum, I could identify a molecule using UV spectra. But then, of course, you already know the structure. And the purpose of this course is to figure out the structures of molecules where you don't know the structure. Now, in your lab, how would you use it? How would sort of an everyday organic chemist use UV spectroscopy? There's lots of different instruments and methods that utilize the features of UV spectroscopy. Let's take a look at this molecule right here. If you take a look at it, you'll see that we have these chiral groups over here. These are in the S configuration. By naphthyl, you think, oh, we could just rotate that bond there and just flip back and forth between two possibilities, whether this group is coming out at me or whether that group is pushed back in. But these hydrogens off of this carbon and that carbon block that transition entirely. These groups cannot interconvert. So you can actually get a bottle of S-binaphthyl and then synthesize this compound from the binaphthyl starting material, and the chirality is not going to change as long as we don't heat things up too much. What we're going to do is we're going to shine UV light on this, and it's going to excite the molecular orbitals, temporarily break that double bond, and when it reforms, it could form in the trans or the cis form again. So we can take something that's pure trans like this and zap it with the UV light, and we'll get a mixture of trans and cis. So this is, of course, work that was done just a couple of years ago, trying to create a system where you could affect the organization of a liquid crystal material by shining UV light on it. So here is the absorbance spectrum of the ESS isomer. So SS refers to the S configuration here and the S configuration here. E refers to the stereochemistry of that double bond. E means opposite. So notice how these two heavy groups are opposite compared to the carboxylic acid groups. So I guess the carboxylic acid groups have higher priority. So the two higher priority groups here on either side of the double bond are opposite to each other. That's what E means. So it's a good time to sort of maybe take a moment and review your stereochemistry from organic chemistry. Now, if we shine UV light on it, what's going to happen is we're going to start to see the Z isomer start to come in. So we're going to be UV spectrum changes a little bit. We're going to start to see a little more. UV spectrum's changing a little bit. You can see how the absorbance, this might have been due to the E isomer, and we're starting to see some absorbance due to the Z isomer start to form here around 400. So obviously the two molecules have different spectra. And now we see a spectra that is the result of a mixture of E and Z. So if you have only two compounds and you're neatly converting from one to another, you'll often see these isobestic points, like one there and one there and one there, which represents the spectra neatly converting from one to another. If you don't have isobestic points, if the crossing points kind of drift, then you probably have a third molecule in there, like an intermediate or an impurity that's forming. So there's the reaction. We go from the E isomer to the Z isomer. And of course, those are important designations in organic chemistry, stereochemistry, so those are things you should review. Now, here we have time, and we have absorbance. And if I should look at a particular wavelength, maybe I'd look at a wavelength close to the peak of this peak here. Maybe I'd look at a wavelength kind of on the shoulder here to watch this grow. Basically, what I can do is I can follow the disappearance of the E isomer and the appearance of the Z isomer, and I can get reaction kinetics. And of course, you can make the integrated rate equation, and you can analyze the whole system's kinetics, get all the free energies, and do it at different temperatures. You can really work this whole system up thanks to the fact that you can follow both the product and the starting material as they appear and disappear by UV spectroscopy. So that's a really useful feature of UV spectroscopy. Now, since it's a chiral molecule, another thing we could do is circular dichroism spectroscopy. Circular dichroism is the idea that circularly polarized light will absorb a little differently depending on whether which stereoisomer you're looking at. And of course, here we see at different wavelengths we have a different effect. So there's a sort of a pattern or a spectrum, if you will. So here we have left circularly polarized light absorbs more, but as we cross the absorbance band, we've come to a region where right circularly polarized light absorbs more. Wherever there's an absorbance band, there'll be these structures in circular dichroism spectroscopy. So it's a highly specialized instrument, but you can actually see the chirality of a molecule. And this spectrum, the shape of this, there's theory that will explain it. But in general, if you know what you're expecting, you can say, ah, there, we must have the SS isomer. If you see the exact opposite, we have the RR isomer. So that's a useful thing to look for. So you can there's a sort of review on how circular dichroism spectroscopy has been used. So if you're looking for more information, you can check up that reference. All right, so we've seen how you can use UV spectroscopy to observe the change in a molecule and follow reaction kinetics. But there's lots of other ways that we can use UV spectroscopy in the modern laboratory. We're not really going to talk about fluorescence today, but that's one aspect of UV spectroscopy, and you can explore that on your own. But I want to talk about how we can connect it to an HPLC, how we can use it to follow the change and structure of proteins with temperature, or say to examine the structure of chiral molecules like DNA, and of course how we can use it to follow superfast kinetics that you could never follow by using more physical techniques. So an HPLC is as you'll be familiar, it's a pump that pumps a solvent through a column, collects it in a sample collector, but along the way it's passing through a detector, and that detector could be a UV spectrometer. And here we see we're looking at a particular wavelength, and we're watching to see if anything absorbs at that wavelength, and over time things start to come off the column and they absorb at that wavelength. But we don't have to look only at that wavelength. Modern HPLCs will have what's called a photodiode array detector, where you're spreading the spectrum across a chip, and at various points in that chip you can look at all the wavelengths that are accessible. So what if we looked at a slightly different wavelength? So here we're looking at 353 nanometers for this particular extract, and if we put it through the column and all this data is being collected simultaneously, just ask the computer, hey, what did you observe at 326 nanometers? And you see the spectrum looks substantially different. So now I see the absorbance at 326 for this peak is higher than at this point here in time. At this point in time, whatever's coming off, the absorbance at 326 is a little lower. So I can definitely tell that this compound must be very different in its electronic structure compared to that compound, because of course we have different behavior at different wavelengths. Now I can ask the computer to show me the spectra at various moments in time. Here's the spectra just under 10 minutes, here it is just past 15 minutes. Notice how the spectra here looks very different than the spectra here. But this UV spectra looks very similar to this UV spectra, so I might expect that both of these compounds, although different, are somewhat related. Now here's the slices I took. Each of these chromatograms was looking at a particular wavelength over time. Well, here's 353. Notice how 353 is the maximum absorbance for this particular compound, and it's lower at 326. But it's near a minimum here and increases greatly when we look at 326. So that's why we had such a different behavior. So I can take any peak in this HPLC, I can ask the computer to show me the UV spectra. If I have a library of UV spectra of expected compounds that might be coming off of my column, by combining the retention time and the UV spectra data, I could probably have a fair degree of confidence about exactly what I have. You can look at these contour plots where we can look at the whole spectrum this way against time this way, and we can see the spectrum for this peak, the spectrum for this peak, the spectrum for this peak. And you can take a slice off of that at any time. So you can combine quite a set of data. These are the compounds that came out of this sort of dietary extract from a rat, I suppose. And so here we have this chlorogenic acid. Notice the polyphenolic compound here. That's going to be your chromophore. You're not going to see a lot of UV absorbance from this, or certainly nothing in the range we're looking at. That's where you're going to get your absorbances around 300. And that's a very different chromophore than we see in this rutin molecule. We still have the polyphenol, but now, instead of being conjugated just to this ester group, it's conjugated through this whole second polyphenolic compound. So you can see why the spectrum here looks very different. And there's a couple of sugars attached to that. The other compound is exactly the same chromophore, So of course we have a very similar UV spectra, but instead of it being connected to two sugars, it is just connected to one. There's just a glucose here. The rhamnose isn't there anymore. So we can get a lot of information from UV spectroscopy combined with HPLC. Another thing we can do is we could use a UV spectrometer like this one here, this Carry 300 Bio, that has a sample compartment where I can control the temperature, and I can raise the temperature very slowly. And I can watch DNA separate from a double-strand to single-stranded form, and the absorptivity changes as we go from the double strand, which is highly organized, all the bases stacked on top of each other, to a single strand, where all those nucleobases are more mobile in solution, less organized, and more free to absorb light individually, rather than the sort of somewhat quenching their total absorbance by being stacked up. So this steep point in the curve here, that is the temperature at which we would call the melting point. And the melting point temperature changes with sequence differences and other characteristics of DNA structures, so we can actually follow or analyze the effect of structural changes on the melting point of DNA. So that's another thing you can do with UV spectroscopy. Here we're doing circular dichroism spectrometry, and here's the CD spectrum of DNA. Here's the CD spectrum of RNA. Notice how different they are. And for proteins, alpha helices have a different CD spectra compared to beta sheets, so you can use CD spectra to estimate the number of beta sheets and alpha helices. And of course, if you're changing a protein, you can follow its denaturation by circular dichroism. Here is a JASCO circular dichroism spectrophotometer. They're, again, a specialized instrument, but they're common in lots of labs. Here we see the denaturation of a protein being followed by circular dichroism. So proteins tend not to have as extensive a change in the UV spectrum, although it can be done, but it is more convenient often to follow them by CD spectra, because you're watching those alpha helices. Follow the alpha helix signal and watch it change, because the alpha helices are going to fall apart as we or will reorganize as we denature the protein. So there's other ways we can use UV spectra. Now, how about following a reaction that is over in a few hundred nanoseconds? That's right, nanoseconds. How would you do that? Well, we can use UV spectra to follow these through what's called laser flash photolysis. Here's time 0, and 1 millisecond, that's 1,000 nanoseconds, is all the way out here. This reaction is basically over at 400 nanoseconds. How could I even mix it fast enough to follow these kinetics? The answer is you can't. But what you can do is you can arrange a molecule such that the reaction can be started by a flash of UV light or light at a particular frequency, and then follow the reaction changes as we watch the molecule turn into something else by observing it at a particular wavelength. So here is a laser flash photolysis device here. That'd be a femtosecond laser flash photolysis device. That's such a fast flash that the actual beam of light that's striking the cuvette is not quite as long as this sample compartment here. It's a really fast flash of light. So here's your pulse of light. This one's lasting 30 nanoseconds, so that's a really long pulse compared to femtoseconds. And we hit it at 308 nanometers, and that is the absorbance spectrum for a particular group on this molecule that leads to that structural change. And then we observe the absorbance at 480 nanometers as it falls away. So we've created a molecule and we watch it change as the reaction happens. So what is the reaction that's happening? This is it right here. We're going to hit this with UV light, which activates this nitro group to a high energy state, and that high energy state is capable of extracting a proton from this corner here and protonating the nitro group. So we just have this rearrangement of the pi system, and the proton is now over here. And now we can do a very rapid proton exchange. This is in water, so this is a very fast reaction. And the next step is going to be then a subsequent intramolecular ring closing here to create this compound here, which then does another fast proton transfer and an elimination to give you the product. So what we're following is we're following the absorbance as it fades away as we go from this more extended pi system to this more compact one, and there's our product. Now, do you think you could predict which of these is the rate determining step? Do you think, well, proton transfer is generally pretty fast, so do you think it's ring closure? That's usually a good slow step in reactions. Or is it elimination? Elimination isn't necessarily fast. Which of these two steps do you think is the rate determining step? I'll leave you to argue that among your friends. You can also look it up in the paper. The reference is at the bottom of the screen. So those are some ways that we can actually sort of use UV spectroscopy in the lab. These are some notes about the slides you've just seen, and that's where I got all the pictures. I hope that you've come to see UV spectroscopy, even though we've not sort of made the case that it's useful for structure elucidation, but that we've shown you that it is really useful in the lab nonetheless, and you should get to know your UV spectrometer and how it works, which is what the next presentation is about. So have a nice day.